Hello everybody. In this video we are going to start looking at electrochemical cells and how we're going to start doing some of the calculations and figuring out what part of the cell would be oxidized and what part would be reduced. So if you remember, we're going to have cathodes and anodes. We're going to have oxidation and reduction happening inside this cell. So quick reminder, remember Leo goes grr or oil rig, whichever one you prefer, but remembering that losing electrons is oxidation and gaining electrons is reduction. Those are going to be important terms because these are the processes that are happening physically at the anode and the cathode. So if you remember, the anode is where oxidation occurs, and the cathode is where the reduction is occurring. What we're going to look at a little bit more today is how do we determine which substance is oxidized and which substance is reduced. So we're going to learn about cell potential. Cell potential is the difference in potential energy between those two places in the cell, between the anode and the cathode. We are going to be able to determine which one is which based on how easily something is oxidized or reduced. We'll be using this symbol right here. E not cell, that's going to be the standard, right? That's what the little circle up top means. So this is the potential assuming you are at standard conditions. Later in the chapter we will learn what to do if you are not at standard conditions, but for now we are. Our data tables that we're going to use are going to assume standard conditions. You'll see that little not symbol. 25 Celsius and 1 atmosphere of pressure is standard for gases. And the big deal for us in this chapter right here is that 1 molar concentration is standard. If you don't have 1 molar, you're going to have to do things a little differently. Kind of like what you learned at the beginning of the year with Hess' law, where you can add equations together. We'll be doing a similar thing here. We will be adding together our cell potentials for each half of the reaction. We'll take the oxidation half, we'll take the reduction half, and we will add those together. One of the things that's a little interesting is that what we're measuring, this tendency for a reaction to occur, is not an absolute value measurement. It's not like grams where we can actually measure it directly. What we're doing is we're measuring it relative to something else. So what we do is we say compared to hydrogen being reduced to H2, how much more or how much less does this other reaction happen? So we are comparing it in relation to an arbitrary one that we've decided. We have arbitrarily decided to use hydrogen. And we set the value, the tendency for it to happen as 0. And we call that the standard hydrogen electrode. You'll sometimes see the abbreviation SHE. Kind of like when they were determining the atomic masses for things, they arbitrarily decided to base it off of carbon and go up and down relative to that, right? Same kind of idea where they picked something to compare it to. So the hydrogen reduction potential we say is 0. And then we start comparing things to that reaction. If something is more easily reduced, if it is more likely, if it has a stronger tendency to be reduced, we will give it a positive value. If it is more likely compared to hydrogen, we would have a positive. If it would rather be oxidized, if it has a tendency towards oxidation, then we have a negative value because it is less likely to be reduced compared to the hydrogen. So it would get a negative number. And just like when we were doing Hess law stuff, if you flip a reaction, you would flip the sign. So if you need the value for oxidation, you would take the opposite sign of your reduction, or vice versa. This allows us to make big charts of reduction values, and you can just change the sign if you need an oxidation value. So you'll see a big chart like this, and you'll notice somewhere on the chart will be the hydrogen, right here. And what do you see? I know it's really small, but if you can kind of look real closely, you would see it's 0. Everything above it is positive. It's more easily reduced. Everything below it would be negative. Less easily reduced, more likely to be oxidized. So what you can do is find each equation on this chart for your half equations, and you can kind of figure out which one is more likely to be reduced and which one's more likely to be oxidized, and that's how you determine which half you're looking at. One thing that's really important, while we do flip the sign, we do not multiply our E value. It is a state function. It does not matter how much you have. Remember intrinsic and extrinsic, right? Some things depend on the amount. Some things only depend on the type. This is one of those ones that only depends on the type of reaction happening. It doesn't matter how much you have. So they love to get people on that. Do not multiply these E values. So let's look here. Let's say that we have a cell that has silver and gold. And we want to know which thing's going to be oxidized, which things will be reduced, which one's the cathode, which one's the anode. We look at our chart and we find these two reactions. And do you notice they're all written in terms of reduction? These are both written on our chart as gaining electrons, which isn't very helpful because one of them has to lose and one has to gain. So we need to know which of these reactions has to be flipped. So let's think about this for a minute. We know that the cathode is where reduction happens, red cat. Which means we're looking for the number that has a larger positive value. Which one is more likely? Which one has a higher tendency to be reduced? Which of these has a higher number? That one. That will be the reduction equation. That is occurring at what we call the cathode. You have your two little electrodes in your beaker, in your cell, or whatever it is you're using, right? And one of them is called the cathode. That means the one with the lower value, the less positive or more negative, whichever way you like to think of it, that's the one that will be oxidized. That's the one that needs to lose electrons so that the gold can gain them. Silver needs to lose them so that gold can gain them. Silver needs to be oxidized so that gold can be reduced. That means this is not written in the correct direction, is it? This needs to be flipped, right? So by looking at our reduction table and comparing the size of these numbers, I was able to determine which reaction needs to be flipped. I was able to determine which one was at the cathode, which one was at the anode, which one is reduced, which one is oxidized, which one gains, which one loses. That will allow me to calculate the cell potential. If I can get these two numbers from my chart and I understand which one needs to be flipped, then I can add those values together. And remember, we do not care to multiply them, right? We don't need that part. The flipping, yes. Direction, yes. Quantity, don't care about. So what we're going to do is take the ones the way they're written on the table. We're going to have our gold needing to gain electrons just like it's written, but the silver is going to be flipped. And if I flip the reaction, I need to flip the sign. I do not care that this has 3 electrons and this has 1. I am not going to multiply this by 3. I only flip the sign. So this is going to tell me that this cell made of silver and gold has a cell potential of 0.7 volts. I add those two values together. That's a very common type of reaction we're going to need to be doing this chapter. Or sorry, equation, right? Adding these values. So our reaction is going to be spontaneous when there's a strong tendency for the things to be reduced and things to be oxidized, right? The higher you go on that table, the more likely things are to be reduced, and the lower you go, the more likely things are to be oxidized. So we can do this calculation to figure out whether this reaction is going to occur on its own or not. Later in the chapter, we're going to see that sometimes they don't want to occur. We may have to force them to happen by plugging them into an outlet and forcing electricity through them. We may have to drive the reaction to occur if it's not going to happen naturally. So the placement on those reduction tables helps us calculate the cell potential, and we're going to come back at the very end, all the way back to our thermodynamics, and start looking to see whether these things are spontaneous or not. Remember in the previous video I mentioned how it's a nice full circle moment? Well, we're going to have that again. We're going to be right back to thermodynamics by the time we're all done, and we'll be right back to equilibrium too. We're going to come back to those things we learned the very first month of school. All right, everybody, that was it for this video. I hope that was helpful. Bye.